Yes, I'm Philipp Gutfreund, and I'm instrument scientist at the Institut Laue-Langevin in Grenoble in France. So we have a research reactor in Grenoble which produces neutron beams, and I will talk about the possibilities we have in surface scattering at the ILL, and I'll show some examples. Mainly one from Dejan. I will, so to say, also talk in his name with this. So we have 4 machines at the ILL, which we mainly use for surface scattering, 3 reflectometers, 2 vertical sample plane reflectometers, D17 and SuperAdam. Both of them can also use polarized beams for magnetism. And then 1 horizontal reflectometer, Figaro. This is the one I'm responsible for, the horizontal sample geometry, mainly for fluid interfaces. And then we have a couple of small angle scattering machines, SUNS machines, and the one we use for surface scattering is D22, because there we have the proper slit collimation available, but in principle this can be done on any SUNS machine at the ILL. So neutron reflectometry can be divided into 3 types of measurements. The most common one, the specular reflectometry, abbreviated NR for neutron reflectometry, is the mirror reflection of a neutron beam from a surface, where the incoming angle equals the outgoing angle, and therefore the momentum transfers only along the surface normal, here called Z direction. And so we probe with this technique only the profile of the scattering length density, in this case along the Z direction in the nanometer range. Then if you relax this condition to have the outgoing angle not necessarily equal to the incoming one, we probe the scattering along this line on the detector, which then also incorporates a little component along the X direction. So we also probe in plane structures, but due to the graziness in geometry, the momentum transfer is much smaller, and we probe larger structures on the micrometer range for this off-specular scattering. And then if we take advantage of the full 2D detector image, then we also probe the so-called G-SUNS direction in Y within plane structures in the Y direction, which are again in the nanometer range. So the first and only example I will go into detail is, of course, from this REACT consortium. Together with Dejan and Rob, they basically sent very talented students, Neha, David, and Emily, to Grenoble for a couple of summers. And they did a great work, and I want to take this opportunity to thank all of them before I run out of time at the end of the talk. And this example is about capillarized infiltration, as David introduced already, but this time it's to produce this nanoparticle polymer composite with a very high loading of nanoparticles. And this then falls, I think, within the water purification part of REACT, with the aim of making membranes. So it's a layer of nanoparticles on top of a polymer layer, and then when you anneal, either thermally or by exposing this to solvent vapor, this is the data I will show now, or also to liquid solvent on top, this polymer starts to infiltrating the nanoparticle layer. And this is a perfect example for specular reflectometry, because by design this sample is stratified. So we will now look at the projection of the scattering length density along the Z direction here. And the big advantage we use with neutrons is we deuterate part of the sample in order to enhance the scattering contrast. So in this case, we deuterate the polymer. So we use deuterated P2BP. And this is the raw data which we get from such a sample in blue before annealing, in red after. You see there are a lot of fringes in the signal due to the interferences at the different interfaces. And we can fit this is the solid line, and then we get this sketching length density profiles along the Z direction. So this is the projection of the sketching length density along the normal direction. So we have the vapor on the left-hand side with a sketching length density close to 0 because of the low density. Then we have the nanoparticle layer here, which is about 300 nanometers thick. And then comes the deuterated polymer layer, which has now a high sketching length density because of this deuteration. And all of this is deposited on a silicon single crystal, which has a sketching length density of around 2 × 10⁻⁶ inverse squared angstroms. So we have a good contrast between the polymer and the nanoparticles and also the substrate. And then we start annealing the system. We switch on the solvent vapor. This was cyclohexane vapor in this case. And then the nice stratified structure, which is the dark blue line here, which clearly shows 2 layers, nanoparticle and deuterated, gets basically smeared out, and we get a gradient. The system is not so well stratified anymore, but we could assume some gradient functions here. But for simplicity, we just assumed 3 layers: the nanoparticle layer on the very left side, the polymer layer here on the right-hand side, and then some kind of intermediate layer. So we fitted this with 3 layers for convenience, but physically we would need to assume some gradient, surely. But fitting it with 3 layers, we can get here the thickness of the top layer, the nanoparticle layer, and its sketching length density as a function of time in minutes. We did this time resolve. Each neutron reflectivity curve took 1 minute to measure. So this is about the time resolution we have. Then the thickness and sketching length density of this intermediate layer, and then the thickness and sketching density of the deuterated polymer layer here. So what we see is that the nanoparticle layer sketching length density increases with time because it gets filled with deuterated polymer. The polymer sketching length density goes down with time because it got swollen by cyclohexane. The cyclohexane was not deuterated, so it has a low sketching length density. In this case, in liquid state, it would be around 1 × 10⁻⁶ inverse angstrom squared. So we have a good contrast between nanoparticle, deuterated polymer, and the solvent. So we can follow the solvent content by watching the sketching length density. We can follow the amount of polymer which goes into the nanoparticle by looking at the residual polymer thickness, and get information from the specular reflectivity. Now, if you go to GSUNS, this was done on a D22 instrument. Here we only have the state before annealing and after annealing. Here the measurements take much longer, several hours, so we don't have time resolution here. So what we see is the direct beam here behind the beam block, the reflected beam, the specular reflected beam, and then the off-specular sketching along this direction, and then the GSUNS. We see here a Debye ring from the nanoparticles before annealing and after annealing. Now we only analyzed this data qualitatively so far. So what we see after annealing, these peaks here, which are mainly related to the order of the nanoparticles. They're here on the around 20 nanometer size. In this size range, we mainly see the structuring of the nanoparticle and not its size. So we see that the ring gets a bit flattened, which means that the nanoparticle layer gets a little bit thicker. But the peaks here, which show the mean distance between nanoparticles, seem to get more defined. So the nanoparticle structure gets better defined in plane and slightly thicker out of plane. But this is only qualitative analysis. We would need to do quantitative fits. I'm hoping for someone, another summer student, to come over to continue this work. So this is the kind of information you get from GSANS. So basically the in-plane structuring of the nanoparticles in this case. And now to finish up, we can not only do this at the solid vapor interface, but also the solid liquid interface. So here are nanoparticles also on silicon substrates in water, and which are covered by lipids. And by a combination of specular reflectivity and GSANS, we could prove that the lipids go on top of the nanoparticle and on the substrate. We can also do this at the liquid air interface, so nanoparticles on a liquid surface, on a liquid water surface, and see the interparticle distance and the size of the particles sticking out of water at the liquid air interface. More demanding, but also possible, is to measure nanoparticles at the liquid-liquid interface. Here, for example, at the dodecane water interface, where signals are very low. Here, measurements take around 12 hours for a single curve. It's very demanding, but it's also possible. And a new development is also solid confinement interfaces. So we can confine a thin layer of any material between flexible membrane and the silicon to also do confinement measurements, and this will be done under shear as well. So with this, I want to wrap up. So I hope I could show you that by a combination of specular reflectometry, of specular scattering and GSANS, we can extract a 3D SLV profile of these systems at these different interfaces. And the main advantage here is using deuteration with neutrons. We have this confinement cell in development, but I missed a lot, of course. For example, with neutrons, you can also probe magnetism very well, because of it has a spin. So this is not my field of expertise, but you can do a lot of more things with neutrons. So I'm happy to answer any questions, and thank you for your attention.